Hello there everyone, welcome to modules 8.2 through 8.4, part 1, where we are going to be working an example of normalization. But before we do that, let's make sure we're all on the same page with some definitional things. So first of all, what is a functional dependency, you might ask? And the correct answer would be that functional dependencies specify relationships between attributes in a relation. They may be semantically obvious, that is, they're described to us explicitly by our business case, or they may be inferred using Armstrong's axioms. Now, our functional dependencies take this form of an expression like A functionally determines B, where we have an attribute, an arrow sign, and then another attribute. So in this expression, A functionally determines B, what do we call A? That's right, we call A the determinant, and we call B the dependent in this functional dependency. Functional dependencies, like I just mentioned, they come from our business rules. So when we have undesirable functional dependencies, we can't just throw them away. We have to continue to accommodate them because it's what the business expects. But we have to figure out how we can make them not be undesirable, problematic functional dependencies. And we do that through the process of normalization. And we know that a functional dependency is undesirable when the determinant in that functional dependency is not a candidate key in our relation. Now, we interact with functional dependencies using Armstrong's axioms, and we're going to quickly go through these, but there's a more in-depth explanation in the previous videos. Reflexivity says that if y is a subset of x, then x determines y. And this is what we call a trivial dependency, because this is just saying that a set can functionally determine any subset of itself. If I know your PeopleSoft ID and your first name, I can use that to figure out your PeopleSoft ID, right? An attribute functionally determines itself. Augmentation says that we can add anything to the determinant, or we could add the same thing to the determinant and the dependent, and that functional dependencies still hold. And transitivity says that if x determines y and y determines z, then it is also true that x determines z. Our inference rules extend Armstrong's axioms just a little bit. So union says if a determinant determines two dependents independently, then that determinant also determines the two dependents together. So if x determines y and x determines z, then it is also true that x determines yz. Our decomposition rule is just the opposite direction. If a determinant determines two dependents together, then it also determines those two dependents independently. So if your PeopleSoft ID functionally determines your first name and last name together, your PeopleSoft ID also functionally determines your first name by itself and your last name by itself. Our composition rule allows us to combine two otherwise distinct functional dependencies. So if A determines B and C determines D, then it is also true that AC, our two determinants together, functionally determine BD, our two dependents together. And then my favorite one to say and my favorite one to do, pseudo-transitivity, is basically like our transitivity axiom, except dealing with a set of values as one of our determinants. So if x determines y and yw determines z, then we could put an x anywhere we see a y, and we could say xw functionally determines z. Because if we know the value of x, we know the value of y, so we can put an x anywhere we see a y. And then to quickly go over our normal forms. So first normal form says we meet the criteria to be in a relation. All of these slides are posted on Blackboard, so you can read these definitions in a little bit more detail. Second normal form deals with this idea of partial dependency. And to be in second normal form, all of your non-key attributes must be fully functionally dependent on the primary key. Okay, so that's full functional dependency. And this is an example of a violation of second normal form. So in this case, if we have AB as our candidate key, and AB functionally determines C and D, well, that's perfectly fine because these non-key attributes, C and D, are fully functionally dependent on the primary key AB. The functional dependency B determines E, however, is not okay. This is a partial dependency because this non-key attribute E is being functionally determined by just part of our primary key AB. So we would need to move this functional dependency, B determines E, into a new relation carrying that functional dependency with it. And we'll see an example of how we do that in just a moment. Third normal form is concerned with what we call transitive dependencies. So to be in third normal form, we must already be in second normal form, so no partial dependencies, but then also we cannot have any non-key attributes that functionally determine another non-key attribute. That is a transitive dependency. And here is an example of that. In this relation, RS is our primary key, and RS fully functionally determines T and U. So that functional dependency is totally fine, but then we have a non-key attribute U that functionally determines another non-key attribute V. So this is a transitive dependency, and this is what is keeping us out of third normal form. So note that RS does not directly functionally determine V. We can only determine V based on RS through our transitivity axiom. Because RS functionally determines U and U determines V, then RS determines V. Okay, but that's a violation of third normal form. So in the last series of videos, we decomposed this relation with all of these problematic functional dependencies into some smaller relations, leaving behind the determinant from the problematic functional dependencies so we could reconstruct the source relation at a later point in time. So here we have another example of how we take a relation with some problematic functional dependencies and decompose it into multiple relations so that we get rid of all of these redundancy issues. So what we have here is an example of a relation and a set of functional dependencies to illustrate a functional dependency that is fine, an example of a partial dependency, and an example of a transitive dependency. So in this case, we have this relation R1 that has these 5 attributes A, B, C, D, and E, and these 3 functional dependencies. Functional dependency 1, which is AB functionally determines C, FD2, which is B functionally determines D, and FD3, which is C functionally determines E. Now, just based on our dependency diagram, it may be readily apparent that A and B are our candidate key, because if we know A and B, we can functionally determine C. If we know just B, we can functionally determine D. And then through transitivity, since we know AB determines C and C functionally determines E, then AB would be able to functionally determine E as well. But I do want to walk through this process of identifying AB as our candidate key, because in other examples, this is not going to be quite so obvious. So we're going to find the closure of each one of our determinants. So in this case, the closure of AB is going to include A and B because of reflexivity, and also C because of functional dependency 1, AB functionally determines C. And then functional dependency 2, well, if AB functionally determines B, then through transitivity we can say AB also functionally determines D. And then if AB functionally determines C, then based on functional dependency 3, that C functionally determines E, then AB can also functionally determine E. Now the closure of B is going to simply be B and D, and the closure of C is just going to be C and E. And D doesn't functionally determine anything else, and E doesn't functionally determine anything else, so the closure of B and the closure of C are not particularly useful. We could also take the decomposition approach to identifying the candidate keys, where we first ask the question, does A, B, C, D, E do all of our attributes together? We know that is going to be a superkey because of the definition of a relation. Does A, B, C, D, E functionally determine A, B, C, D, E? And the answer to that is always going to be yes. So now we're going to try to remove one attribute at a time from this superkey. We're trying to reduce it, and every time we ask, can that reduced superkey functionally determine the attribute that we have removed? This is the decomposition approach. So we're going to try first removing this attribute E, and we're going to ask the question, can A, B, C, D functionally determine E? Okay. Looking back at our functional dependencies, we'll see in functional dependency 3, if we know the value for C, then we can determine E. So the answer to this is yes, meaning we do not need the attribute E in order to functionally determine every other attribute in the relation. So we know that A, B, C, D is also a superkey. So we can try to reduce this one step further and ask, can A, B, C functionally determine D? Well, based on functional dependency 2, if we know the value for B, we can use that to functionally determine D. So A, B, C, yes, that can functionally determine D. Okay, try to reduce this one step further, and we ask, can A, B functionally determine C? Well, that's right there in functional dependency 1, that A, B functionally determines C. So the answer to that is, of course, going to be yes. Now we're going to try two more reductions. Does A functionally determine B? Well, looking at our functional dependencies, it doesn't look like anything functionally determines B except B. So we have to keep B in our determinant. And then we're going to ask the other question, does B functionally determine A? And the answer to that is, again, no, because nothing functionally determines A except A. So through the decomposition process, we've identified A, B as our candidate key, just like we did in the synthesis approach. Okay, so your synthesis approach and your decomposition approach should both find the same set of candidate keys. And in this case, our candidate key and none of the attributes that make up our candidate key are dependents in any of our functional dependencies. So this is going to be our one and only candidate key. Okay, so now that we've really determined that AB is our candidate key, let's see about resolving these undesirable functional dependencies. So what we want to do is decompose this relation R1 to get rid of any of our undesirable functional dependencies. So functional dependency 1, AB determines C, is fine because AD is our candidate key. Okay, what we're concerned about here is functional dependency 2, where B functionally determines D. We have a non-key attribute, D, which is being functionally determined by part of our primary key. So that is a partial dependency. Okay? So the thing we do to resolve that partial dependency is we're going to create a new relation, and we'll call it R2 in this case, that contains the attributes that are part of this undesirable functional dependency, and we bring that undesirable functional dependency over here into this new relation. Now the relation that we started with, R1, we're going to remove that functional dependency and the attributes, except we want to leave the determinant of that functional dependency behind, and that's going to be a foreign key in the new relation that refers back to that attribute in the relation that we removed the functional dependency from, so we can still recreate the source relation. So now relation 1 is ABCE with these functional dependencies of AB functionally determines C and C determines E. Okay, so now at this point we have these two relations. So in relation 2, our dependency diagram looks like this. We just have B and D, and B functionally determines D. And in relation 1, we have A, B, C, E, where AB functionally determines C, and C functionally determines E. Okay? So relation 2 is in third normal form because all of our non-key attributes are fully functionally determined by our primary key, which in this case is B. Now in relation 1, we do not have any partial dependencies any longer. We have no non-key attributes that are being functionally determined by just a part of the primary key. Okay, so we are in at least second normal form. However, we have a transitive dependency, which is a non-key attribute functionally determining another non-key attribute. Okay, so think back to the transitivity axiom. AB functionally determines C, and C functionally determines E. So AB only determines E through this rule of transitivity. So that is our violation of third normal form. So at this point, relation 1 is in second normal form, while relation 2 is in third normal form. Okay? So the way we resolve this third normal form violation is just like how we resolved the second normal form violation, in that we are going to create a new relation that contains the attributes from this problematic functional dependency, C and E, and we bring that functional dependency over into this relation, removing that from our source relation, right, and leaving behind the attribute that is the determinant in that functional dependency. Okay, so now from our source relation 1, let's erase all this. I'm going to rewrite that. So now relation 1 has only these attributes A, B, and C, and this one functional dependency of AB functionally determines C. And our dependency diagram is going to look like this. And our dependency diagram for relation 3 is just C and E, and it functionally determines like that. So now all three of these relations are in third normal form because all of our non-key attributes are being functionally determined by the entire primary key. We don't have any partial dependencies, and we don't have any transitive dependencies. So this is going to get rid of our modification anomalies. This is going to get rid of any redundant data. But then we're able to reconstruct this relation because when we moved these functional dependencies out to new relations and we left the determinant behind, now in these new relations, B is a foreign key that refers to B in relation 1. And in relation 3, C is a foreign key that refers to this attribute C in relation 1. Okay, so we can reconstruct this original relation right here that we started with because we leave behind the determinants in the functional dependencies that we move out. So that's it for this example, and in the next video we'll go through identifying candidate keys using synthesis and decomposition. See you there.